on this one, right? So you agree my tangent lines, look at them. They're positive, but they're getting bigger, steeper, right? Steeper means bigger. So I think that that red graph would suffice on the right side, wouldn't it? What about the left side, though? So if I come over here, this is a small negative number, isn't it? Which means as I go this way, I need to have a slope that's negative, right? Or sorry, I said negative. Why did I say negative number? Man, this is a bad Monday. I said this is a small negative number. That is not a small negative number. That's a small positive number, right? It's above the x-axis? Yeah. Okay, this is a small positive number. This is a small positive number, but look, they're getting bigger, right? So as I move this way, I should have positive slope. Positive slope. And as I go this way, my slope should be getting steeper. So what's it going to look like? Down, like this. See if that makes sense. If I pick a point here, my slope is what? Very small and positive. If I go to the left a little bit, that's going to be still positive, right? But bigger, steeper, bigger number. So big Y value means steep slope on my original graph. Y'all making these connections? I'm wondering if I should do another one or not.
Yes.
Do one more?
Yes.
Okay. Let's see. Let me look at something real quick. Okay. And I kind of didn't draw that very good. These go up like more like this forever. This is the derivative. Sorry, this is the derivative. I want f. Is there anywhere where the slope of the tangent line is 0?
At 0.
At 0. At 0, the slope of the tangent line is 0. Okay, so I can put it anywhere. You want this one up here this time? So I know that my original function should have a slope of a tangent line that's 0 there. Tell me what's happening to the right of this function. My tangent lines are what? Positive and small, right? But then they're getting bigger. So that means as I move to the right, I should have small positive slopes that get bigger. So it should go like this. Like that? Yes? Small positive numbers getting bigger positive numbers. Small positive numbers getting bigger positive numbers. See, on this one, you're not looking at the actual pitch of the line, right? You're looking at y coordinates. Here, you're looking at pitches of the line. Okay, what about over here? Small positive, small positive, small positive, getting bigger. So as I move this way, it's going to do this again. Because look, these are small positive numbers on this slope and they get bigger as you move to the left. So this is very similar to this, isn't it? Not so interesting. We'll do one more. How about That's your derivative. That's your derivative. So anywhere where the slope of the tangent line is 0. Right here and here, right? Okay, I'm not quite sure where they are. I'm going to just try this. I'm going to go here, and I'm going to put this, I don't have to put it the same level as the other one. I can put it here. I just know that they have slopes of tangent lines that are 0 there, right? Now, what's happening to the slope as I move to the right from this point? I'm going to go positive, small positive, and then they're going to get bigger, and then still positive, but the slopes are getting smaller, back to 0. Yes? So positive slope, big positive slope, back to small positive slope. Maybe something like this. Small positive slope getting bigger, smaller. Oof. That was tough to squeeze in there. Y'all see what I did? Do I have a small positive slope here? Is it getting bigger? Okay, and then once I get here, what happens? Still positive slope, and then it tapers out to 0 again. Now that I know what I'm trying to draw, I might even come back in here and redo it to give myself some room to, like that. Like that, to me, is a better picture. Yeah, a better representation of what's happening. On your homework, what you're asked to do is match a graph to its derivative. They give you a graph, they give you derivatives, you match them. It's a little easier than this. Okay, so let's talk about what's happening here. As I go to the right, my slope should be what? Positive. Should start out small and get bigger. So like that. And then what about over here on this side? Small positive getting bigger as I move this way. So it's going to go like that. All right, you get to play with that at home for your homework, all right? Let's get back to the notes. In the spirit of Valentine's Day, I remember, this is so stupid, but I remember when I was first started teaching here, I had an office mate. He was kind of an idiot, but I shouldn't say that, but he doesn't work here anymore. And he was being real cheesy, and he said that, and this was right around Valentine's Day, he said, I'm going to tell my girlfriend that my love function for her, that its derivative is always positive. And I was like, well, what are you trying to accomplish with that? And he said, well, that means that my love is always growing for her, right? Is that what that means? If the derivative is always positive, that means that the function is always increasing, right? So imagine trying to draw a graph. Now let's say our function's value was here. It wouldn't matter if it was there, but if this was always positive, right, everywhere, then that means my slope must be a little bit pitched like that. Anywhere I pick, right? So if I pick a point to the right of this, I'm going to have to be above that point. Why is it impossible for my next point or any point over here to be below that point? Imagine the point was here. Then that means somewhere between here and here it had to come down, right? Which means the derivative would have had to have been negative at some point, right? And if you're saying that the derivative is always positive, always, right, then the graph of that function should always go up. And so it seems initially like this is a very, very sweet statement, right? But it's not, because I can give you an example of a function that satisfies that condition, but doesn't do what he was trying to say. So if you have a function that has a horizontal asymptote, like this, you can asymptotically approach that dotted line without ever getting there, but your slope's always going to be positive. See, because as you move to the right, you are going up. But it is possible to move up towards something and never get there forever. You'll never, ever get to that line. So this does not mean that your function grows without bound. It is possible that you could be bounded above. So I had to break the news to him that this wasn't a strong enough condition that if he was really going to impress her.
Did he ever show you anything again? The divorce?
No. The divorce papers, yeah.
You were taking off his
No. No, we were talking about that, and yeah. Is it, I mean, if that makes you think a little bit about the functions, right? Like, is that condition strong enough to say that it continues to grow forever? That's not enough. You need more than that. Okay. See, if I ever presented my wife with something like that, she would tell me to shut up. Just shut up. Okay. All right, these are more examples. Pardon?
Does she have math background?
No, she doesn't like math. Yeah. All right. Okay, so we have some alternative notations for derivatives. So this is because in different fields, chemistry, physics, they have different notations, but mostly because Isaac Newton and Leibniz, the two people who came up with calculus, they use different notations. So that's why we have at least two, all right? But other fields use different things also. So we need to understand that all of these are equivalent. So if somebody gives you y is a function of x, that if you see f prime of x, it means the derivative. If you see y prime, just y with that little prime mark on it, that means the derivative of that function. If you see dy dx, it means the derivative of that function. If you see df dx, it means the derivative of that function. If you see d dx with the function written next to it, it means take the derivative of this function, treating x like the variable. So I want you to notice that in all of these notations, in the denominator, that x is the independent variable. The independent variable. Remember with functions, you have the dependent variable and the independent variable. The independent variable is the one that's being plugged in. The dependent variable is the y. Y depends on x. So this tells you what your independent variable is, okay? This one right here, capital D, take the derivative of the function, all right? This one is interesting. D subscript little x, same thing. That's your independent variable. That notation right there is used in Calculus 3 because in Calculus 3 you actually start looking at things that are functions of more than one variable. So instead of plugging in just x, you plug in two things like x and y and it spits out a z. And then your function, if you're trying to find rates of change, it's different. So you have to be very clear on what variable you're differentiating with respect to. And so that notation becomes important. This notation is fine for Cal 1, but it starts to become a little bit bad later on. All right, so this notation, when you have dy dx, like any of these, dy dx, df dx, d dx, all that is called Leibniz notation, named after Gottfried Leibniz, one of the co-founders of calculus. And we'll see later on that his notation is actually pretty good for some applications. It's better to have his notation. All right, a definition. A function f is said to be differentiable at a if the derivative exists at a. So why is it that the derivative could not exist? Well, the derivative is a limit, right? And when we first started studying limits, we saw that we could get answers, like we could get the limit of that is 4, or we could get infinity, or negative infinity, but we sometimes got does not exist, right? And it is possible sometimes for a derivative not to exist. And I believe the example I gave you of the absolute value function was the first example that I drew on the board, where the derivative looked like this. That derivative did not exist at 0. All right, it didn't. So if it does, right, if the derivative exists, then we say that it's differentiable at a. A function is said to be differentiable on an open interval I if f prime exists at every point in I. So we have the idea of the first one, differentiable at a point versus differentiable on an interval. Differentiable on an interval means you have to be differentiable at every point inside that interval. All right, now this very important definition. Differentiability implies continuity. If your function f is differentiable at a point A, then f must be continuous at A. Careful, this does not say continuity implies differentiability. So let me try and give you a visual of what's happening. Let's say I have some function and I tell you at some point that the derivative exists, that the slope of the tangent line exists. This theorem says what? If it's differentiable there, which means that the slope of the tangent line exists, then it must be what? Continuous there. That means when I draw the actual function, from the left it must come to that point, and from the right it must come to that point. That's what the theorem says. The theorem does not say that if you're continuous you must be differentiable. And a great example of that, of this right here, is that absolute value function. Can you draw this absolute value function without picking up your pencil? Yes, it is continuous, right? But is it differentiable at that corner point? I showed you the graph of it. It doesn't exist. So continuity does not give you differentiability, but differentiability does give you continuity. Is that fair? Okay, it's a theorem. You just have to take it on faith. All right? So I just gave you an example of a function. This function f is continuous on negative infinity, infinity. Do you agree? This function is continuous on negative infinity, infinity. You can draw without picking up your pencil. But f prime does not exist at x equals 0. Do you agree? At that point. Now, does the derivative exist everywhere else? Yes? There was a very, I'm not going to say it was an important problem, but mathematicians like to ask questions that are often useless but profound. A question was asked, is there a function that exists out there that is continuous everywhere? You can draw without picking up your pencil, but nowhere differentiable. So this is an example of a function that's continuous everywhere, right? But it's differentiable everywhere except one point. Is there a function that's continuous everywhere and nowhere differentiable? Like you go to any point on the graph and you cannot take a derivative. That was a question.
Kind of be like that.
Like a jigsaw kind of, not like a saw blade almost, like a bunch of these.
Mm-hmm.
Well, this would almost work. It wouldn't be differentiable here, 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 right?
Well,
But everywhere in between it would.
like remember the oscillating one? Like we couldn't take the limit of it because
Oh, that sine function?
Yeah.
That sine one that went like this?
it's a limit, right?
Went like that. This function right here, this would actually be differentiable everywhere because these are curves. What we need for non-differentiability is sharp corners like this. So a saw blade would almost work, but see, you would be able to take derivatives. In all those green points, you would have derivatives because those are little straight lines. So this eluded mathematicians for a long time until they actually found the function. It's called the Weierstrass something function. Weierstrass. Anyway, what it is this. I can bring it up if I have time, but it's this idea, okay? It starts out, it's like a saw blade like this, okay? And then if you zoom in and you zoom that one little section up like this right here, it would look like this. Okay, so that's this zoomed out, or zoomed in, understand? And if you zoom in on one of these, it's the same thing. And you can keep zooming forever. It's an infinite number of serrated, little serrations on this graph. And it's in, y'all want to see it? Okay. Unfortunately, I mean, we'll be able to graph it probably. Let's see, Weierstrass function. Oh, let's see what happens here. Oh, there it is. Look at that. We'll trust Wikipedia. There we go. There's the graph of it. So they zoomed into just one little piece of this, and you can see it's like a repeat of what you're seeing here. But where's the actual function? Hold on, I want you to see what it is.
See if I figured it shit out. I don't even know I figured it out.
Where is it? Oh, there it is. Okay. There it is. This is the function right here. That's it right there. Now, it's a cosine function, all right? And then this right here is a calculus 2 thing, so you don't need to worry about it too much. I'll just tell you basically what it means. What you're going to do is you're going to take a cosine function and add to it another cosine function, and add to that another cosine function. And there's actually an infinite number of these cosine functions listed out. So this is an infinite series of cosine functions. And if you graph it, it will create this. But you can show mathematically that the derivative does not exist anywhere. That's harder to show. You can't do it by picture. You have to show it like with the definition. You take the limit at any point and you show that the limit doesn't exist. So it is possible to have a function that you can draw without picking up your pencil, but you can never take the derivative of it. But it's a pretty special function. All right, I'm off topic. Let me see here. All right, so the question becomes, when do functions fail to be differentiable? When does it happen? And there are 3 major places where a function would fail to be differentiable. I know we're kind of at the end of class. I know it's a Monday, but these 3 things you do need to know for sure. Okay, anytime you have a corner or a cusp at some point, it is going to fail to be differentiable there. So for this, for part 1, I'll give you some graphical examples. Here's a corner. It would fail to be differentiable at that point. That's the absolute value. A cusp would look like this. At that point up there, it would fail to be differentiable. And I want you to understand why it's not differentiable. Look, if you were to the left of this point, do we have slopes of tangent lines? Yes. And they are all what? Negative? And then I get to here, and immediately I switch over from negative values to what? Positive values. So it's like the derivative does this immediate jump from negative to positive. So that's going to create a break in the derivative graph. Look at this one right here. My slopes are what? Positive. And then really steep, getting huge, and then all of a sudden, really steep the other way, negative. So again, it does this switch from positive to negative at an instant. So is this function differentiable right here? Yes. It's only there that it's not. So this is a cusp, this is a corner. All right, anytime, part 2, there's a jump in the graph. So if we have a graph like this, and it jumps, it's not differentiable at that jump. Now, the reason why it's not differentiable is because if it were differentiable, it would have to be continuous. That theorem said differentiability implies continuity. So if you tried to convince me that it was differentiable here, my argument would be differentiability implies continuity, and this is not continuous. So jumps, and then the third one is a little harder to realize, but let me draw it. I'll draw it slowly. Okay, take a look at this graph. We have positive slope, right? Positive slope, getting steeper and steeper and steeper, and then it goes like this. Okay, so let's take a look at that tangent line. Slope is positive, getting big, 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 big. And then it becomes vertical. What is the slope of a vertical line? Undefined. And that means your derivative is undefined. So at this point where we go vertical, where we go straight up with the tangent line, we have non-differentiability there. And then once we get past that, then we start curving again. So we get a really big slope, but it's, it's a number. So it's impossible to have that vertical tangent line, or a number for that vertical tangent line. So the slope is undefined, so the derivative is undefined. Okay? Corners, cusps, jumps, and vertical tangent lines. Oh, what? I must have added that later. Is that in your notes? I don't think those are in your notes. Wow, I actually created it.
You went in the future and then came back.
I created it, and then what did I? You can zoom in on this. Oh, yeah, you can zoom in on this. And no matter how far you zoom in, it just gets uglier and uglier. Yeah.
Oh my God.
So there's the function. Okay, higher order derivatives. Since f prime of x usually gives us a new function, I say usually because, again, you can have a derivative not exist. Since it usually gives you a new function, we could, again, find the derivative of that function. Couldn't we? And we could do it over and over and over. We have special notation when we're trying to take the derivative more than one time. So here they are. F prime of x is the first derivative, which is what you have been doing. F with two primes means you're going to take the derivative of the f function, get an answer, and then take the derivative again. That's your second derivative. The third derivative would be 3 primes. So that means take derivative of f, get an answer. Take that derivative, get an answer. Take that derivative, get an answer. That's your third derivative. And then once we get to the fourth derivative, we stop writing the primes. Obviously, we can't continue to write primes. So we write a 4 here, but notice that we put the 4 in parentheses. That's critically important. Let me explain why. Let's say that I tell you that you have this function f of x equals, let's go with sine x, all right? Then if I write f for x like that, what I mean is take the sine function and raise it to the 4th power. If I write f with the parenthesis around the 4, that means take the 4th derivative. That means take derivative of sine, then again and again and again, 4 times. So we have to have some way of distinguishing between these two notations. So this means 4th derivative. So do you remember this? Do you remember what I was saying about that, the love function? By the way, if you want to impress your partner this year, you want to use this, you can steal this. Here's what you need. If you want to get rid of that asymptote possibility, right, that I was telling you about, then just add this condition. If you add that condition, you're in business. That is some serious love right there. Okay? That is love that grows without bound. Now, I haven't explained why, but we will get to this. If your first derivative is positive, you're increasing. That for sure, but you can asymptotically increase. The second derivative being positive actually means that your function has to be what we call concave up, which means it has to have a shape to it that looks like, well, it either looks like this or like this. It's got to be one of these two. And it can't be this one. Why can't it be this one? Well, because the first derivative has to be positive, which these are decreasing, right? So you have to be this one. And that one curves up, and it does not have an asymptote. It's not possible. So that's the one. That's the one he was talking about. All right, so fifth derivative and so on, right? We can keep going? Now, using the other notation is a little more complicated. The Leibniz notation. So I'm going to write this second one. It's d2y over dx2, like that. That's the notation for the second derivative using Leibniz. And there's a reason why these 2's are offset. See how it's d, then 2, then y, and then dx, then the 2? Because if you write both the 2's, like if you wrote 2 here and 2 here like that, then someone might think you mean dy dx squared, which would mean take the first derivative, get an answer, and square the answer, instead of take the derivative 2 times. Do you see the difference? So this, we don't want to be using this notation, so we offset the 2's so that you don't accidentally try and square something. And then, of course, you do the same thing with 3, and then 4, and then you could keep going forever. All right, so we've seen, or at least I've told you, that if you're given a position function, that the first derivative gives you speed, right? So if you have a position function, s of t is s equals f of t is linear displacement or position of an object as a function of time, then the first derivative of the function is your velocity function. So this creates a velocity function, instantaneous velocity. Now, if we take the derivative again, that means if you take the derivative of the velocity function, what are we going to get? Let me try and illustrate this. If I have a function here, here's time, and here's distance, then this right here is your f of t, right? That's your original function. It tells you where you are at any point in time. Yes? Yes. If I take the derivative of that, I'm going to graph it. This will be time, and this will be velocity. Yes? And now I'm trying to figure out what would happen if I graph the second derivative. What will this be? All right? So let me try and show you where you can get it from, because this actually works for anything that you do. What is distance divided by time? What's that divided by that? Velocity, right? Distance over time is speed or velocity. So doesn't this right here comes from taking that and dividing it by this? So shouldn't this right here come from taking this and dividing by that? And velocity over time is acceleration in physics. You've probably seen acceleration like this. How many of you know the acceleration of gravity? You've probably seen it in physics, negative 9.8 meters per second squared. Have y'all seen that before or heard of that? If you haven't, don't worry about it. But let me try and help you understand what this is. This is meters per second. That's what that is. Now, what is meters per second? Meters is distance, right? Seconds is time. So meters over seconds, just that top part, is velocity. Velocity divided by time is acceleration. And so what they do is they just take this s as an s over 1, and they flip it up like that, and you get your s squared. So if I take this velocity and divide it by time, I get my acceleration. So you're always going to have distance over time squared, whatever the unit time is squared. So our second derivative gives us that acceleration function. So that's what this says. I'm running out of time. All right. Let's, in 5 minutes, let me pass around the sign-in sheet. I'm still going to do one more thing, but let me get the sign-in sheet so you can at least... I don't think I did the sign-in sheet last week. So just sign in. Sign in for anything that's missing. Okay, here you go. Okay, how many of you remember this from college algebra? I don't know how many of you saw this, but we have d of t equals negative 16 t squared plus v naught t plus d naught. Does anybody remember seeing that formula? It looks familiar? This is the formula that we use if you have an object on Earth and you drop it. If you take out air resistance, this gives you the position of the object after a certain amount of time for all objects on Earth. Because hopefully you know that if you drop a feather and you drop a rock, they should fall the same. If there's no air, they should fall the same. That weight doesn't matter. So that's the actual formula for it. What I'd like to do real quick is I'd like to take the derivative of this. What is the derivative of this? Well, you would have to do that limit, right? You'd have to do the limit. I'm not going to do it. I'm just going to tell you what it is. That's what it would be, all right? And then if you take the derivative again, twice, again, I'm just going to tell you what it would be. You get negative 32. That's all you get. Now, in this formula, t is seconds, and d is measured in feet. So this answer right here is feet per second squared. Now, I'm going to get my phone real quick, if I can find it. I'm going to ask Google something. What do I say again? Hey, Google.
Hey Siri.
Right? What do I say?
Okay.
Okay, Google. That's right. Now you're listening. Convert 32 feet per second to meters per second.
32 feet per second equals
9.754 meters per second. So it actually, if you convert this over to meters per second, this is the acceleration of gravity. Do y'all hear me? So it turns out, this works on any planet, okay? If you can measure the acceleration of gravity on any planet, you can actually go backwards from this back to velocity and then back to position. And that's called doing antiderivatives. We do that in Cal 2. So if you start from here, you can go back and recover this function, which is pretty cool. Here, all I'm showing you is that if we start with this function, we can come up with the actual acceleration of gravity on Earth. Yes?
Can we do all derivatives like that? Or we just kind of take the power?
Can you do what?
All derivatives like that, or just take the power away?
Oh yeah, I'm going to show you that. Yeah, it's going to be real simple to take derivatives later. We're not there yet. All right, try your homework for 2-1. And was that 2-2? Yeah, that finishes 2-2. So make sure you do your homework for 2-1 and 2-2. And I'll see you on Wednesday. Is Wednesday Valentine's Day? Oh, isn't that so sweet?